Hello, this is a talk on challenge-based learning in science and math. So why don't we start out doing a scientific experiment? What object will fall to the ground faster, the orange or the piece of paper? So upon seeing this phenomena, surprised or not surprised, what question comes to mind which might lead to an explanation of the observed phenomena? Keep that question in your mind, and we'll come back to this later. About 2 months into my first year of being an elementary and middle school science and math teacher, and after the shock of the responsibility and the workload and the intensity of all wore off, I realized I was actually bored with the subject matter I was teaching. Yet I'm a scientist and a teacher on this planet. I should be one of the most enthusiastic disciples of science around, able to impart wisdom and knowledge and love of this topic and connect us humans to our physical universe. But I was always beginning my class this way. Let's study density, kids. Let's learn about the atom, kids. Let's study parallel and series circuits, kids. Let's dive into the conservation of mass, a key tenet in all of chemistry, kids. No wonder both the kids and I were bored. When prompted with an opening to class like that, what are the kids supposed to say? Like, no thank you, I have something else to do, or maybe tomorrow. No, they're kind of forced to study these topics that they have no prior knowledge about, no context to dive into with. It's just, they're kind of forced to do it because the teacher is kind of suggesting that they do it. Their goal is to make it through the day, check the necessary check boxes to advance, and already the point of learning is lost. And there are three main tenets which, if all satisfied, good learning can happen. And all of these are missing in the way I was introducing my classes. Number one, kids should have a choice. Number two, they should feel like they can succeed. And number three, they should be able to see how the topics they're pursuing are connected to the greater whole. All of these were missing. So way back in another era, like 10 years ago, when I was first starting out in the teaching profession, I decided to run an experiment. In 2009, I advertised to a group of parents that I was going to run a 1-week camp on quantum physics for middle school kids. 10 12-year-olds joined me on a quest to uncover the mystery of the atom. And why not? The greatest scientists in history who uncovered the very nature of every atom in our universe adhered to a set of practices championed by the NGSS, by the American Science Standards. NGSS is the Next Generation Science Standards. And the NGSS mandates that all American kids excel at these science and engineering practices. And our curiosity was that if kids do these same practices, could they come to the same conclusions that the greatest scientists in history came to? In other words, if the greatest scientists in history employed these science practices and came to these grand theories of the atom, could our kids employ the same science and engineering practices mandated by the NGSS, or the NGSS believes they can do it? If they did this, would they be able to come to the same conclusions that scientists like Niels Bohr and Albert Einstein came to? This was the experiment. And even if we answer these questions, a problem still remains. How can schools, micro schools, small learning groups bring these experiences to kids in a sustained manner? How can the ceiling be lifted on what we would expect from kids, not just to know, but what we'd expect them to be able to do? The years and years of research underlying the NGSS say it's possible, and that the practice that professionals do, kids can do too. So can we sort of make this happen, make this standard, make this normal in school and learning settings? Let me back up and let's talk some actual science. So upon seeing this brilliant display, I would just let you know that each flame is being produced from a different chemical. And then I would say, what questions come to mind? What questions are arising for you? And I bet the simple, obvious question is like, well, why do different chemicals produce such different and such brilliant colors? And if this is a question you had, you're already on the same path that early physicists were on to solve the mystery of the atom. This is precisely the phenomena that led to the quantum physics revolution in the early 1900s. So if this is the question you had, You're already on the same path early physicists were on to solve the mystery of the atom. This is precisely the phenomena that sparked what would become the quantum physics revolution that came to a fore in the early 1900s. And if you're ready to do this, if you've already asked this question, you're ready to take the next step and go into the practices championed by the NGSS, again, which they believe and I believe and we all believe that kids can do. And these are, and I'll just read them, asking questions, developing models, plan and carry out experiments, investigations, collect data, interpret data, construct explanations, and make arguments from evidence. You may even be willing to do some math. And that's called for in the American Science Standards, and I think it's awesome. So here's what's going on. You are encountering a challenge. A problem was brought to you. Something intriguing, something captivating, something compelling was brought to you. And this is what we educators must do. This is the first step in challenge-based learning. Challenge-based learning in science and math requires a compelling question, a compelling problem, or a compelling challenge. In contemplating the difference in those brilliant colors emitted by the different chemicals, which was the question which prompted and gave way to the quantum physics revolution, was the same question we posed to that experimental group of kids 10 years ago in a summer camp on quantum physics. And from that challenge, these kids were off and running. Here is another example of a problem being brought to kids. Upon seeing this explosive reaction, the students came up with the driving question themselves, came up with the challenge themselves. What is the chemical reaction which resulted in such a dramatic explosion? An entire course on chemical reactivity flows out of this driving question. Here, students conducted this experiment on day one of a camp, which essentially elicits the key challenge for a full course on electricity. And the question is, or the challenge is, why does this happen? It's a simple question. Incidentally, the mystery of electricity in history began this way. It was a study of static electricity that led to the entire field of electromagnetism. This course, the whole course was set in motion for the entire phenomenon of electricity to be mapped out. Every lab, every activity needs a challenge. Every course needs a challenge. Kids have to have a challenge. Immediately there is excitement and buy-in. What is the nature of water that does this? Do other liquids bend like water? What if I don't rub the rub? What if I rub it with different materials? What does the rubbing do? Should I try different cloths? All these questions will lead to the standards and content being covered. You know, we don't care about that. We'll get it done, do it anyways. But the brilliant thing is the kids are off and running just like authentic, just like real scientists investigating a phenomena. And sometimes merely seeing something beautiful can elicit a challenge. So here kids ask, and here the obvious question is, why do these rocks have such straight edges? And students are ready for an entire course on mineralogy and crystallography. And from here, guess what? The students are ready to ask questions, develop models, plan and carry out investigations, collect and interpret data, construct explanations, make arguments from evidence, and they may even do some math with you. And this idea that you start out with a challenge, this was not my idea. This is not something invented at Quantum Camp. Researchers have explained the ultimate drivers of fostering intrinsic learning, intrinsic motivation, which lead to unfettered pursuit of knowledge. And I touched on these three things before. There's a sense of choice, a sense of competence, I can do this, and a sense of how it relates to the greater whole. Why is this important for my community? How does this benefit our community? And there's actually a social element to that third point too. Is like, will this be enjoyable to do with my classmates? So once you see a challenge, once you contemplate or recognize a problem, and it's grabbed you a little bit, it's captivated you a little bit, you're ready to dive in, investigate. And this is where learning, in courses and curriculum really takes off. And so, back to those original topics that bored the heck out of me and bored the heck out of my kids, density, circuits, the atom, conservation of mass. So how do we go about teaching those things without just introducing them without any context? So therein lies the answer. You have to build, create, manufacture the context and the curiosity so that kids want to dive in. And that's just simply what curriculum designers should be doing. That's the charge of a curriculum designer, is to create the interest, not just map out a set of recipes, but generate interest, generate curiosity. And so this is where compelling challenges come in. This is where you bring compelling, captivating phenomena to the kids. And again, once they see that, they're off and running. They can jump through the standards and pursue a wonderful experience in science. So I know, especially in like project-based learning, there's this organic wish. There's this dream where kids organically just dive into the subject matter they need to learn without any compulsive words or even encouragement from the teacher. And I'll provide like a hypothetical example you actually read about in project-based learning books. And so it goes like this. The teacher noticed a group of kids gathering by an aquarium at the back of their room. They were talking about the fish and the other animals, and one student observed that there were far fewer snails in the aquarium than there were at the beginning of the year. Interesting. So the teacher, after letting them talk for a while, gently intervened and inquired about the conversation. The teacher saw the students had formed a good driving question already about why there were fewer snails, and already had ideas on planning and carrying out investigations. So these kids were already diving into this science and engineering practices. The students then spontaneously and organically have launched into their own grand project-based learning unit on discovering the key elements for sustaining life, a standard. There was choice. The students felt they could succeed, and clearly it was collectively deemed important to the entire community. The kids were talking about it, enjoying it, and enjoying the conversation together. They solved the problem. The snails were dying. In reality, this is not a likely scenario to occur. Science teachers know they need to cover a certain number of topics each year, and there's little chance students will organically gather around an aquarium just at the right moment the teacher wants to do a lesson or do a unit on what it means to sustain life. In other words, if you want to study the atom, you can't wait for kids to just organically start lighting chemicals on fire. If you want to study density, you can't wait for kids to randomly drop various objects in water, alcohol, and oil. That would be amazing if they did that. Saw some things float, some things not float, some things sink. Bam, you can go off on a lesson plan on density. And if you want to study the conservation of mass, you can't wait for kids to run experiments in open systems and closed systems, where in open systems the mass changes, in closed systems the mass doesn't change. The chances that they're randomly going to just start doing this, that you can just swoop in and run the lessons that you want to run, is, I think, pretty unlikely. Back to that camp in 2009 that we run, that experiment with those group of middle school kids who were eager and bold enough to go learn about the atom and solve quantum physics. By the end of the camp, some of the kids had asked, after doing a week's worth of experiments, and all these experiments were just repeats of what was done in history, the kids were literally asking the same question that Niels Bohr asked in 2013, or at least he published the results in the year 2013. And Niels Bohr was contemplating, how can an electron, a subatomic particle, move from here to here without inhabiting or occupying any space in between. So the data suggests that these quirky subatomic particles leap in quantized lurches. Our kids were asking, does this mean the electron leaps in these weird lurches? And I said, I don't know. It looks like that's what the data suggests. And of course, that's what Niels Bohr and Albert Einstein were wrestling with back in the early 1900s. And so, just to sort of recap that idea, in that experiment, these young kiddos set out to uncover the nature of every atom in our universe. And they saw a problem. They saw the challenge of explaining those differences in the different colors of light emanating from different chemicals. So they knew they had to study light. They knew and this led to the experiment. This led to studies and experiments on waves, because light's a wave. They knew they had to learn about color. What is color? What's the origin of color? What's the physical origin of color? These kids were happy to investigate that huge challenge. They knew they had to learn about energy and heat. And out of these studies, they rediscovered the nature of every atom in our universe. And as 12-year-olds, this quirky, lurchy, lumpy behavior of the atom is now normal to them. And so if you talk to any 18 or 20-year-old first taking a quantum physics class in college, it's beyond nonsensical. But if you're like 13 or 12, and this is, your early exposure to physics, it's not nonsensical. It's just what it's just what the universe does. So what is the scientific challenge that paves the way for kids to discover big ideas? As curriculum writers, curriculum designers, as educational programmers, the key is to find the problem, find the challenge, pose the challenge, give it to the students, and the students will solve it if they have the equipment and the lab equipment to go ahead and do it. And they'll solve it with each other, collaboratively, socially. They'll be talking, having fun, and by the end of a lesson or by the end of a unit, they will have discovered some big ideas. And along the way, they'll be doing what scientists do. They will be doing what the NGSS says that kids should do. And again, I'm no big fan of standards, but the NGSS standards are actually, I have to admit, I'm chagrined to admit, pretty good. And the kids in any of these pursuits will be asking questions, developing models. They'll be planning investigations. They'll be collecting data, interpreting data. They'll be constructing explanations and making arguments from evidence. And they will even do some math to make sense of their data. It's extraordinary. And back to the paper in the orange. The question that we arrived at was obviously, why do both objects clearly of different masses fall at the same rate? If a student asks that question, if you pose that challenge to a kid, you have a physics course ready to roll. And if you arrange your lesson plans, if you sequence your challenges right, you have a course which will bring the kids to discovery of nothing less than the universal law of gravitation, put on the map by Isaac Newton in the late 1600s, which basically explains the trajectory of all the planets, the moons, the Earth around the sun, just in one simple, beautiful theory, which is represented through an equation. Our students discover that simply by going through a series of challenges. And again, they solved the problem, they solved the challenge. They believed they could solve it. They believed they could have success. They saw why it was cool, why it was relevant, that it could be a collaborative endeavor, and technically they had the choice to pursue it. So there's three critical things: choice, a feeling of success, and a feeling that it benefits the community, are all there in this challenge-based approach. And it all started with a challenge. What we say at Quantum Campus, every lab needs a challenge. And the beauty of this approach is that it can be done, in a more conventional setting, led by a teacher. We do live online classes where we send kits of supplies home to kids so they can, do the lab work prompted by a particular challenge. And the challenge is posed in a live online setting by a teacher. And so this is a great way to, do challenge-based science. But also, these can be video-driven and self-paced and self-guided. So we've developed a set of videos where the Quantum Camp teacher poses these challenges. We actually get the kids started in lab by videotaping the actual experiment getting started. We may not finish the lab. We may not provide all the information. We want to leave a lot of mystery to the kids to figure out and solve. But then, of course, we don't want to let misconceptions linger too long. A little bit's okay. Struggling through some contradictions and misconceptions is good. But of course, at the end of every lesson, at the end of every unit, we provide the kids through videos in these self-paced modules what the accepted science is over the past 2 centuries or 1 century. And so whatever data, whatever conclusions the kids came to, that's good, as long as it's like kind of somewhat rooted in evidence, somewhat rooted in their data. That's okay. No data is perfect. It is challenging to come up with arguments to back up your claims. That's all good as long as they're trying and improving. But regardless, after every lesson, we'll share what the accepted science is, what the accepted logic and arguments were in the history of sciences, by the great thinkers and scientists in history, and how they arrived at what you might find in textbooks or Wikipedia now. And so this is the essence of how science and math, and we run math the same way. Math can be broken up into just a set of challenges, and out of these lab challenges, students arrive at formulas, relationships, mathematical patterns. So it can be all done the same way, and it's just very easy then for kids to pursue these key critical topics, science and math, in a way that doesn't burden small learning communities, micro schools, homeschooling families. And so, yep, I want to thank Meridian for inviting me to give this talk. My name is Michael Finnegan. I'm the founder and CEO of Quantum Camp. And please feel free to reach out to me anytime. I'd love to talk with any one of you at any time.